Hello everyone, welcome to this session on Poisson distribution. We have been seeing about theoretical distribution in a continuous session of videos. The first thing which we covered was binomial distribution. The next one to follow suit will be Poisson distribution. We will quickly move on to define what is meant by a Poisson distribution, what are its nature, and how can it be practically put to use. The probability mass function. Why do we define as a probability mass function? You call it as probability mass function because Poisson is going to be a discrete random variable. So you apply a Poisson distribution for a discrete random variable. So the probability mass function for a Poisson distribution will be given of the format probability of capital X taking the value small x's e power minus lambda power x by x factorial, x valid for 0, 1, 2 up to infinity. So we said that in our prior video binomial could be applied to cases which are going to be frequently occurring in nature, like whenever the number of trials is going to be less than 20, then you're going to apply binomial distribution. Now what's the case for Poisson distribution? Poisson will be applied to cases when you have the number of trials to be more than 20. That's why we can see over here in this range, your x moves from 0, 1, 2 up to infinity. Rather in binomial, you would have moved from x varying as 0, 1, 2 up to n. So the difference between a binomial and Poisson is going to be the number of times you are going to perform the action or the number of samples in which the actions are going to be performed. When n is going to be finite in nature and it is going to be very small in number, rather say n is going to be less than 20, then you go for binomial. So when n is going to be more than 20, the number of trials become more and more, then we choose to a Poisson distribution because this gives us more accurate answer than a binomial. So what happens when the case that n is equal to 20? So when you have the case that n is equal to 20, both a binomial and Poisson will give you the same answer more or less, with just a few places changes in the decimals. So in and around 20, positively like 19, 18, 20, 21, 22, in all these of the cases, both binomial and Poisson will give you more or less the same answer. But when it moves beyond this, so when you have more number of quantities to be explored, like 50, 100, 1000 people you're going to take, and then you're going to find what are its effects and so on. In which case, which is more suitable when n tends to infinity, the more suitable one will be your Poisson distribution. Now x is going to be the quantity which is going to be random variable which we are going to explore on. Apart from x, the only script which is available over here is called as lambda. Lambda is called as the parameter of the distribution. So why do we call it as a parameter? Once this value is known to us, then everything else will get fixed for us. We don't want any other information apart from this lambda to fix a Poisson distribution. So in which case we say x follows a Poisson distribution with parameter lambda. And the nature of the parameter lambda is such that lambda is always greater than 0. It remains to be a positive quantity. Now, knowing learned about the probability mass function, the next comes the important point of what are going to be the statistical averages which are going to be related with this Poisson distribution. So what do we mean by the statistical average? Is going to be mean of the random variable and variance of the random variable which follows Poisson distribution. We can see the nature that the speciality of a Poisson distribution is such that the parameter is going to be lambda, the mean of the Poisson distribution is also lambda, and the variance is also lambda. So now the case is such that the parameter, mean, variance, everything happens to be one single entity called as lambda, which has a nature which is going to be greater than 0. So once this quantity lambda is known or fixed, then everything is going to become an easy job for me. So practically this is many application for our Poisson distribution. since it is easy to evaluate, its statistical averages are quite easy and it is going to be similar for your mean and variance. Coming to the next part, when we try to move from binomial to Poisson, or we say that n is equal to 20, in and around all the cases are going to be one and the same. Binomial and Poisson are working in the same way. So you call this to be limiting cases. So what is meant by limiting cases? You can see the Poisson as an expanded version of your binomial distribution, or you can see your binomial to be an extension, Poisson to be a restrictive case of a binomial. So there are going to be three limiting cases under which a binomial problem can be considered to be a Poisson problem, or you can say the binomial moves towards Poisson. So what are the three cases? Case number 1, as n tends to infinity, the number of trials is indefinitely large. As we said, x varies from 0, 1, 2 up to n for a binomial, and whereas in case of Poisson, 0, 1, 2 up to infinity. So this becomes, or it becomes larger and larger. This n becomes larger and larger, then the binomial will move towards your Poisson distribution. Number 2, what is going to be case number 2? As p tends to 0, what does p stand for? Normally p represents the probability of success. So we know that the range of probability always lies between 0 and 1, and probability associated with 1 is going to be that for a sure event, and probability associated of 0 is going to be something called as an impossible event. So impossible event will have probability 0 and sure events will have probability to be equal to 1. Over here in this case, we say that as p tends to 0, then binomial will move towards Poisson. So what is actually happening over here is the probability of success is becoming very, very small, in which case for an impossible actions or impossible action, so there is nothing such like a impossible action, or then we can say that it is going to be rarely happening actions, rarely happening events. Okay, in which case I can apply a Poisson distribution to get more accurate answer. So whenever you have the situation of rare happening of an action, something like finding an error in a page of your textbook, or associating an aircraft accident that is going to happen across a city, or something of which is going to be once in a lifetime or once in a kind, then in such case a rocket launch kind of thing. So it is going to be rarely happening action, it is not going to be happening day in and day out, then in such cases you apply Poisson distribution. The next one is lambda equal to np is going to be finite. We already know that the mean of the binomial distribution is going to be np, and we saw in our previous slide that the mean of the Poisson distribution is lambda. So when they become one and the same, then what will happen? We have both of them to be the same, so I have np equal to lambda, the mean becomes finite. So in cases where a Poisson distribution is going to be defined but you don't know what is going to be the parameter lambda is unknown, then I can say that if n and p are given to me, then I can find lambda by making use of the formula lambda equal to np. This can in turn be used to estimate the number of times the action is being repeated, like n can be estimated as lambda divided by p, or you can estimate your p to be equal to lambda by n, more vice versa. All these quantities can be computed if this one relationship is more applicable and more suitable. Now moving on, we will try to put everything which we have now learnt in a nutshell. Like Poisson is going to be a case where you apply it for a rarely happening event and when the number of trials are going to be more large in nature, and the probability function is e power minus lambda lambda power x by x factorial. So keeping these few tips in mind, we will move on to solve problems. The first problem is like the number of monthly breakdown of a computer is a random variable having Poisson distribution with mean equal to 1.8. The point to note dear, so the mean of the Poisson distribution has been given as 1.8, and more priorly, the first and foremost thing to note, it is going to follow a Poisson distribution. So what we have over here is x follows Poisson distribution with mean lambda, and lambda value has been given as 1.8 because we know that mean is the same as lambda as 1.8. So find the probability that this computer will function for a month without a breakdown, with only breakdown, with at least one breakdown. So the problem we are dealing is breakdown, how many times the computer crashes and stops working. So this is something which we often see, means then it's time for us to change the computer, or if it is something we can push upon, then the probability is going to decide on how can we change and when can we change. Now let x denote the number of breakdown of this computer. Then what happens, the first one you want is probability of without a breakdown. Without a breakdown means x is equal to 0. So it is e power minus lambda 1.8 to the power of 0 by 0 factorial, because we know that the probability function is e power minus lambda power x by x factorial, and we know that lambda is 1.8. So go take out your calculators, estimate the data, get it to be equal to 0.1653. Next, moving on to the second subdivision, we know that probability of only one breakdown, probability of x equal to 1. So how to fix it? E power minus 1.8 to the power of 1 by 1 factorial. Note down children, over here we have something called a 0 factorial. 0 factorial is always equal to 1. Please don't make it as 0 and then push your quantity to infinity. Keep in mind 0 factorial is 1, and the next one 1 factorial is going to be equal to 1. If you don't know the factorial button is available in the calculator, you can do it, or we have already said in the tips for calculator, this expression totally can be fed as an input to your calculator, and the value can be estimated for each values of x which keeps on changing. Now when you are going to give x is going to be equal to 1, you get the value of 0.2975. And third one to go on with at least one breakdown, at least one. So you have one or more than one. So 1, 2, 3, 4 and so on. So that is going to be 1 or more than 1. You cannot move till infinity because your x tends from 0 to infinity. So the other way of computing is go for the complement, probability of x strictly less than 1, and we know the number which is strictly less than 1 is going to be 0, and we have very well calculated this value over here. So 1 minus 0.1653, so taking the negation of it, we have it to be equal to 0.8347. So this completes the task of finding the probability using a Poisson distribution for the case 0, 1 and x greater than or equal to 1. For key tip, if you want to key in on the quantity e power minus 1.8 to the power of x by x factorial in your calculator, then you can go for e, which is given by shift and a log. You can use a power button, use minus 1.8. This is going to be multiplication, which is a default for us, but tell the calculator with the multiplication sign, then go for a 1.8, go for a power button, and this x, how to input this x? Alpha and the script x, then you will have happening this capital X to take place, and then there is a division sign over here, and then x factorial. So x factorial button will be present over here in your calculator on top of your x inverse. So use your shift and x inverse, then you will find your x factorial. So when you are giving this as an input in your computation mode, and then you use your calc button, you will ask for your prompted for your x, input 0, get the value of 0, input 1, get the value of 1 with equal to and 2 and so on. So this can be effectively done using a calculator in a single stroke. Have fun dear. Thank you.